had so many Black Friday ads and things for Desert Book with Squares. I'm like, oh my gosh, that's
All right. Let's go ahead and do a quiz.
Hooray.
Yay.
Oh.
This is still an experiment. So, what? Quiz 001 should be online. And you need to use the access code 127 to open it, hopefully. If it doesn't ask for an access code, let me know.
Oh, that's so many good choices for this.
I know. It does go in the grade book though, so
I'm not
really
really
want
best
to answer correctly.
it's not really basket.
5 minutes.
Are we sure this is an advanced?
Yeah, that's basket. Good time for the quiz. So it's quiz 1, it's on Canvas, the access code is 127.
You know, just to mess with this data, because it says you will get
So much is
100%.
still this.
Yeah,
For
I think it'd be like my duty.
Yeah, but it's actually going in the grade book, so you don't want to do that to yourself.
I have 4 minutes and 20 seconds to settle this quandary.
I mean, this could be.
But you can do it multiple times too, in those 4 minutes.
As long as the
This
best
is
answer
true.
gets the get after the last
But
one.
it'd be a
Thanks a
great
lot.
effort of trolling in the fact that there's one student who didn't pass your 100%
Yeah.
foolproof test.
So if you choose basket, we can
And
also
there's
choose
been some students who don't have access, so they're just gonna get 100%. But the goal is to make sure that people who get onto Canvas can handle the Wi-Fi, that the Wi-Fi can handle a room full of students.
I like that it randomly puts the correct
That's,
answer in different
yeah, yeah, it
positions.
rearranges them.
You should have put some other random ones, so
Yeah.
we all did some basket weaving. Someone should totally weave a basket in this class.
Some people probably do. I took an algebraic geometry class, and one of the students was sitting in the back and knitting a sweater the whole time. She was way beyond the subject, but it was her advisor who was teaching, so she was coming in just to hear him talk and pick up whatever she could, but mostly she was knitting sweaters. It was cool.
If counting to 100 over and over again helps you pay attention.
Yeah.
I think that would get distracting.
All right, so is everybody good with getting onto the quiz? Okay, cool. Finish that up in the next 5 minutes, but I'm going to keep lecturing.
Oh, you have to hit submit, don't you?
It's only 1 point. So.
Yeah, I downweighted it since we hadn't gone over that question yet. So. All right, I need a better marker. That's good.
This is policy 224.
That's sweet.
Oh, yeah.
That's Just because the course number changes. I've been going to this school on and off for a long time. The course numbers change a lot. Like some of them have to have ampersands in the course number now. I don't understand why they have to use it.
Why they would?
Well, some of the courses, since they've changed and remodeled things over the last while, have gone to get ampersands in the course numbers.
Yeah, the ampersand is like, I think, a statewide numbering system.
Like for if it's been changed course number too many times.
Yes.
No, I think it means it's a number that other institutions make sense of. All right, so let's talk about addresses.
Notice in the error from compiler, it treats addresses as ints. Like it just calls it an int.
Yeah.
Not funny.
Yeah, addresses are asexual. All right, so we can have an integer x equals 5. We can have an integer pointer called y. If I say y equals 10, I'm going to say false, most likely. Because this said y is a pointer to an integer, it did not give a value to y. It simply said y is the address of something in memory, something that's an integer. But, oh, let me back up. All right, let me back up. If I do this, I'm saying take the thing pointed to by y and set that equal to 10. This will probably say false. Because at this point, y is probably either 0 or it's just random gibberish. And so doing this will not make sense. Now, doing this may give me a compiler warning, but this will work. This will set y to have the value 5. If I choose to use y as the address of something, this will probably give me a segfault now, because memory address 5 is not likely to be a valid memory location. But if I do something like this, y equals the address of x, and then I say the thing pointed to by y equals 10, what is this going to do?
What is the address 10?
It'll change the x to 10.
It'll change x to 10. This is saying y is the address in memory where x is stored. This is saying take the thing that y is pointing to, that location in memory, and set it equal to 10. Well, since y is pointing to where x is stored, this says go to the location where x is stored and set it equal to 10. This is a long-winded way of setting x equal to 10. It's goofy to do here, but this is what we do with subroutines. So, integer x equals 5, integer answer, answer equals twice x. And my function called twice is just going to double its argument and return that. So if I have a main program like this, set x to 5, answer is just an integer, call twice, pass it x, store the result in answer, this should set answer to 10, twice 5. That's the easy way to return a value from a function. But if you want to return more than one value, or if you want to do something with that value more sophisticated, here's what we can do. We can change this to say, pass a pointer to an integer. And maybe I'm going to make this void. And I'm not going to return anything. What I'm going to do is I'm going to say, the thing pointed to by that argument is equal to twice times the thing pointed to by that argument. And over here, I'm going to just say twice address of x. Okay, what is this going to do? This sets x equal to 5. It's an integer. I pass the address of x to a subroutine. My subroutine is expecting the address of an integer. It takes the thing at that address, that's going to be the value that I passed it, which is 5, multiplies it by 2, that's 10, and then it takes the thing that that argument is pointing to and sets it equal to 10. Right? Star A is x. And I'm passing the address of x So A is the address of X. This is the thing pointed to by A. That's X. So this is saying X equals 2 times X. But if I just passed X as an integer and I said X equals 2 times X, that doesn't affect the X up here because we passed the value. If I pass the address, I'm actually passing a location in memory by value, and it's using that location in memory to read the old value, double it, and then store that double value back in that location. So this is what we do when we want a function to change arguments. We pass the address and we use this dereferencing of these pointers. Yeah?
Do the parentheses matter?
I don't know. I've never tried it without. Because then it would look like 2 star star A and it would just get confusing. They don't hurt, but they probably don't matter. But I picked an unfortunate example.
When it's just the star A on the left, I usually don't put it, but if it's the 2 star star A,
Yeah. Star A on the left will
for
definitely
your own
work by itself.
sanity.
Right. All right, so we have a way to take the address of something. We have a way to dereference a pointer, to take the thing pointed to by something. And we can go back and forth with those. So what does this have to do with structures? Let's make a simple structure. Let me call this vector. So think of 3-dimensional geometry, Cartesian plane. So you have points that have x, y, and z coordinates. And we can think of those as vectors. So we'll do some physics here. So draw a line from the origin to x, y, z. That's a vector in free space. So to describe a vector, we just need to know its x, y, and z coordinates. This is integer physics. That's really goofy. All right, so we define this structure. Now instead of passing around x, y, z, x, y, z, x, y, z, a, b, c, w, x, y, we just pass around an object of type vector, right? So here's what our main program might look like. Struct vector v. All right. We would like to set each of the components of this vector to 0. In other words, we'd like to do v dot x equals 0, v dot y equals 0, v dot z equals 0. It turns out it's really common to want to zero out a vector like this. So I would like to make a function called 0 that I just pass a vector to, and it sets the x, y, and z components equal to 0. Okay, here's what my 0 function looks like. Void 0. Struct vector, we'll just call it arg. And that's what I'm going to do. So let's do this. I have confidence that it'll come up. All right, so I'm just putting in this code. So I'm going to declare my struct vector to be integer x, y, z. Struct vector v. So void 0. And I'm going to pass a struct vector argument to this. And I'm going to set those fields equal to 0. And I'm going to make a print routine.
Arg.x.
Yeah. So I'm going to make a print routine that takes a struct vector and I will print out the 3 fields inside brackets with commas in between them.
Do you want to define the vector outside of main or inside of main?
I'll define it outside.
Would it work if you did?
No, it wouldn't find it.
Okay. That's what Ken framed.
All right, so I got a vector declaration, declaring B to be a vector. I'm going to zero out, and I'm going to print it. I honestly don't know what this is going to do. But let's find out.
Oh, you got the F.
I forgot. Compiler happy, we'll prototype our functions. So it compiles, and I run this, and there's my vector. And it has not been zeroed out. And why has it not been zeroed out? There's a 3-word answer. Pass by value, right? When I call my 0 routine with V, it does not pass V, this actual variable. It passes the value of it. So it creates a new structure, and it sets its fields equal to whatever the fields of V are. And this is working on this new structure. Just like when you call a function and you pass it an integer, your function creates a new integer that's equal to the value of the integer that you passed. So when I'm manipulating the fields of arg, I'm not manipulating the fields of V. Right? This is no different from that twice program that we had. The problem is we're working on a copy as opposed to working on the actual piece of data. Well, since data structures are key to everything we're going to be doing, what we're going to need is the ability to actually somehow get a hold of the pieces of this variable itself, as opposed to simply their values. So here's what we're going to do. We're going to pass the address of V, and when we print, we can just print V. We don't need to change the values. But since we're trying to change the values of the field, we've got to pass the address of it. And our 0 routine is going to say, give me a pointer to a struct vector. And then over here, we're going to say star arg dot x, y, and z. Everybody on board with what we're trying to do? So we'll pass a vector pointer. So we'll do address of V when we call 0. We'll pass struct vector star arg. And we'll zero out the thing pointed to by the arguments fields x, y, and z. And so now it works fine. since everything we do in this course is going to involve structures, and we're going to have programs that change structures, combine structures, create new structures, we're almost always going to want to pass around the addresses of structures. Which means we're going to write things like this a lot. And typically we're going to have a structure, and some of its fields may be integers, they may be doubles, they may be characters, but some of its fields will probably be other structures. And some of the fields in those structures may be other structures as well. And so we may end up doing something like the thing pointed to by arg, take the x field, take the thing pointed to by that, and take the subfield, and take the thing pointed to by that, and take the real field of that. And this is horrifying. So we have a shorthand in C. And the shorthand is as follows. Star arg dot x, we can write that as arg arrow x, where the arrow is a minus followed by a greater than sign, so it looks like an arrow. And star arg point y, we can just write as arg arrow y and arg arrow z. And this means the x field of the structure pointed to by arg. Okay, this means the x field of the structure pointed to by arg. And now if that field itself is part of a structure, and we want to manipulate a field of the structure that that's pointing to, it's going to look like arg arrow x, arrow sub, arrow main. We're a few weeks away from doing this practice, but I want to set you up for it. And it's going to make a lot more sense when we work with these arrows. So we can do the following. So we can just write that. And that should still work. We spelled that correctly. There you go, fourth try.
Try.
All right, so have you seen that in 121, the arrow notation? That's really for when we're working with data structures, right? Otherwise, you can always get away with this. But when you start putting these things together, this is a whole lot more convenient. All right, any questions up to here? So we're going to shift gears. A lot of what we do in computer programs is we try to sort things. We always want things sorted. I don't know why, it's something about humans. Right? We alphabetize things even though the alphabet's order is completely random. There's no reason A comes before B. We just decided it does, so we alphabetize based on that. But it helps us find things. And the other thing we do a lot of is we do a lot of searching. So sorting and searching are two key topics in any data structures course. And we're always concerned with how quickly things run. So there are more and less efficient ways to do sorting or to do searching. And in a few weeks, we'll spend a lot of time going through a lot of different sort and search techniques, and we'll cover more of these in 223. But let's start with sort of the most basic approach. Suppose we have an array that can hold 100 integers. And you're reading data. You're reading scores as they're coming in. If somebody scores something, they type in the next score. And you want your program to record all of these scores. And then you want to be able to look at the scores in sorted order, from lowest to highest. Well, let's say that the scores that you're grading are 90, 87, 100, 74, 86, 85. So that happens to be the order in which the person's going to enter these scores into this program. Well, one thing you can do is you can just make a loop. Read in the first score, store that in x0. Read the next score, store it in x1. Read the next score, store it in x2, and so on. At the end of this, you'll have 6 scores stored in x, and then you can call your bubble sort routine. Sort those out, print them. Okay? Bubble sort is really inefficient. We talked about order of complexity a little bit. It's an order n squared. If you have 10 times as much data, bubble sort takes 100 times as long to run. If you have 1,000,000 times more data, it takes 1,000,000,000,000 times more to run. Okay? A different approach would be to try to keep your array sorted at all times as numbers are being input. You got some time while the person's typing in these numbers anyway, so let's take in these numbers and keep our array sorted. So here's what x looks like. Okay, if we do this first approach, x0 we store a 90, x1 we store an 87, and then 100, a 74, an 86, and 85. Okay, that first approach is really, really fast. It doesn't matter how long this list of numbers is, it takes us the same few number of operations to store a new number. We just go to the next entry in the array and we copy the number there. But our list is unsorted. Now, if we wanted to keep our list sorted, here's what we could do. Let's take our first number, we'll store that in the beginning. Our list is sorted because it only has one number in it, 90. Our second number is 87. Well, if we store an 87 here, our list is out of order. Where should the 87 go? Should go in element 0, right? But we've already got something in element 0. So what we can do is take this 90 and move it down and store the 87 there. Now we get 100. That goes right here, that's fast. But now we got a 74. That should go in element 0, but that's full. And we can't just move element 0 down to here because there's already something here. So we'd like to move that down to here, but we can't because there's already something here. So we'll move this down to here, well that'll work. So this will become 100, this will become 90, this will become 87, and this will become 74. That was a little bit more expensive. Now we get an 86. Well, that should go right here. So again, we have to move all of these things down and then store the 86 there. And then we get an 85, and that should also go up here. So now we've got to move all of these things down and store the 85 there. And this is a problem with arrays. We want, ultimately, our array to look like this. Did I make up grades? No, those are right. That's what we want our array to look like. But if we have a gazillion numbers in our array and we decide we want to insert a new number in the beginning of the array, we've got to move everything down. And the longer the array is, the more expensive that is. But it's unavoidable with an array because when we say x, That's the address of the first thing in the array. And based on that, there's exactly one location where the second number in the array can be. It's this address plus 8. And the third number is exactly this address plus 16, and so on. Arrays pack things in memory, one after another after another. And if we want to squeeze something in the middle, there's no space to do it. We can't have x bracket 2.5. All right, we can have 2 or we can have 3, and if we want to have 3, we've got to move everything else down. So arrays are a really simple object to work with, but they're fairly inefficient. And they're really inefficient if you want to do insertions into random locations. And similarly, if we wanted to delete a number from our array, well, you can't actually delete something from memory. Memory always has 1s and 0s in it. We could set it equal to some magic value like 42 and say that's deleted, but that's not really an option with integers. The only way we can get rid of this is if we move everything up in memory. And then instead of saying we have 6 numbers in this array, we'll say we have only 5. So deletions and insertions in arrays can be expensive operations. All right, what can we do about this? We can use an array, but instead of storing just integers in this array, we're going to store some extra information. So imagine an array okay, so we want to insert the number 77. We would like to somehow squeeze it in right here. We don't want to move everything in the array. So if we have 1,000,000 numbers in our array and we try to insert in the very first spot, we've got to move 1,000,000 things. So we want to somehow squeeze this 77 in here. But this is the first element in the array, this is the second element in the array. There's no option for element 1.5.
Out of curiosity, and maybe this is an answer, but can you just say for each element past this point, can we just add 1 byte to the memory address? Just move it forward one position. Instead of having to copy and move and stuff, can we just add
That's kind of where we're going. It would be hard to somehow tell the system that in the future this is at this other location instead of this location it used to be at. But that's
More like a
effectively
hash
what we're
table or
going to do. Yes. So here's what we can do. So this is x0, x1, x2, x3, x4, x5. So before we've inserted this new number, we have 6 entries in our array. And now we want to insert a 77. Okay, there's this understanding that the way that we pull the numbers out of this array in order is 0, 1, 2, 3, 4, 5. Instead of trying to force this into here and move everything down, what if we simply said, we're going to store it down here in this empty location. And now we're going to change the order in which we pull things out of our array, like this. So somehow we're going to keep track of the fact that the first number in our array is index 0, but the second number is at index 6. The third number is index 1, 2, 3, 4, and 5. So now when we pull things out, we're going to get 74, 77, 85, 6, 7, 90, 100.
Is like the updating of this sort of string of variables, is it more efficient than, constantly writing them down? Oh.
Because what did I have to do? I had to go from this to this. I had to squeeze a 6 in here in the beginning somehow. And that would seemingly be as inefficient as what I was trying to do in the first place. But there's a trick we can use. So here's the key to all of this. this. Let's get rid of our 77 for now. We're going to store a pair of things in here. We're going to use something other than an integer. We're going to use a pair of integers. We're going to store the piece of data, and we're going to store the location of the next piece of data. So the next piece is 85, and that should be followed by the data at index 2, which is 86, which should be followed by the data at index 3. 87 is followed by 90, which is followed by 100. And down here, I'm going to store a -1. And -1 means there is no piece of data after this. Well, I don't need my length variable anymore. I can start with the first element, 74, and I can say, okay, the next number is index 1, that's 85, followed by 86, 87, 90, 100, and that's the last element in my data. Okay, now, what do we have to do to insert 77 in this list in order? Go down to the next free spot in our array, store a 77 there. We want that 77 to go in between here and here. So let me do this as a before and after. So after, this is what we're going to have. Let me copy the before first. All right, we're going to store the 77 at the next available location, which is down here. We want it to come right after the 74, so we're going to say 74, instead of being followed by index 1, is followed by index 6. So now 74 is followed by the number 77, and the number 77 is followed by index 1, which is 85. So now, when I go through my list, I'm going to find 74, 77, 85, 67, 90, 100. My list is in order. How expensive was it to add this new number? I had to store it here, I had to change this, I had to change this. 3 operations. And no matter how long my list is, I can insert anywhere in that list with 3 operations now. Okay, this is called a linked list. And it's the first sort of real data structure we're going to work with beyond arrays or struct statements. And it's like an array, except the things can be jumbled up as to where they actually are in physical memory, but they still allow us to access the data in a particular order. So now, let's say I want to delete let's delete the 86. Well, 85 was pointing to 86, 86 was pointing to 87. All I got to do is that. Change 85 so that it says the next element in our list is 87. And that points to 90, that points to 100, that's the end of our list. And we deleted something from the middle, and it took a small fixed value. It's a really powerful way to organize information. Yeah?
How do you change the first item in the list?
That's a really good question. So if you want to change the first element, so let's say we want to insert 70. Well, we could put a 70 down here, and we could have that point to this thing. But somehow we have to know when we're using this list that the first item is actually down here rather than up here. We need something that tells us where the first entry is. And that's kind of quirky. So here's what we're actually going to do. The first entry in our array is not going to be one of our numbers. It's simply going to be there to point to the actual first number in the array. So this would point to, we don't care what the data is, but it's going to say 1. So this is going to be 74, 85, 86, 87, 90, 100. All right, so there's our original list. We insert an 87, or 77, so the 77 goes down here. 74 points to 77, 77 points to 85. So now if you want to insert in the beginning of the list, so insert 70, put a 70 down here, we change this to point to node 8, and we have node 8 point to node 1.
That way, when I load up that list, it'll start knowing where to start.
Yep, so we always look at 0, but we don't actually do anything with this number, we just use this to find where the first node is. This is called a sentinel node. Sometimes it's called a header node. And it's there to avoid special cases, basically. Same thing if we want to delete the first entry in a list. With a sentinel node, it's no different from deleting any other. If we want to delete the 70, we just change this to be a 1. Over here, if we wanted to delete the 74, we have to do something strange.
What if we want to delete the last element?
Say again?
What if we want to delete the 100?
The 100? So 90 pointed to the 100. Just change that and say it doesn't point anywhere, that's the end of the list. All right, got the basic idea. We're going to expand this a lot over the next few classes. But this is going to be the gist of programming assignment 1. You're going to implement a linked list using this approach. So we're going to have to define a structure that stores a piece of information and also the location of the next entry.
Why are there two, let's say -1 on the end? Or is it just a way of?
Because I deleted this node,
Okay.
so I changed this thing to say that's the end of the list. But this thing is still sitting here. There's always something in memory, right?
And there's just no need to go and change that.
There's no need to go and change that, but we would like to be able to reuse this the next time we want to store a piece of information. So we're actually going to need a third piece of information, which tells us whether or not this thing is actually part of our list or not. In other words, has it been deleted? So the next time we need a location to store something, we might go ahead and store it right here, because we know that 6 isn't being used. All right, that's the setup, and like I say, that'll be programming assignment 1. That's actually due 2 weeks from Wednesday. It's an exception. Instead of being due on Friday, I'm pushing it back. I think it's on Canvas. All right, I'm going to leave it at this because this is a good stopping point. Go ahead and do the online assignment. If you can't get to it, shoot me a note or come find me in 126 around 3 o'clock.